Welcome, Bourbon. Welcome, Justice.
Hello.
Welcome to our room. What's going on, people? Surprised to see me here so early, huh? I'm absolutely chilling. Don't even have a collared shirt on today. Not even a Hawaiian shirt. That's how chilling I am. How are people's weeks shaping out? Here's a question. Do you even live your life by weeks anymore? Or is it just kind of one constant stream of days? Life, but it feels different these days to me.
Yeah, more like this second option.
like the good news, I mean, it's weird because like weekends don't feel as weekendy, but weeks also don't feel as weeky. like if it's Sunday, it's gonna be Monday. Well, I love my job anyway, but you don't want to do on Monday. It's not like, oh great, like Monday here just feels like, oh, I'm not leaving the house anyway. I just have to pretend to be productive for an hour and a half, and then we're good. And then I can go back to being in my pajamas. Even though I hate that, I don't have my pajamas, but I could and I want to. The point. Well, anyway, even if it just says 3. Oh, there we go. Safa's joined. Now it's a party. What's up, Safa?
What's up, Professor? How you doing?
We almost started without you. I'm doing pretty good. Thank you very much. I'm doing pretty good because today we're finally going to go over the thing. I've been promising we were going to go over for like 3 or 4 days now of class time. And 3 or 4 days, that's like 3 or 4 business days. Well, we don't really do business here. What that would do? 3 or 4 math days, which is like a week in actual time. We're finally going to go over it today. Yeah. Am I the only one excited about this? Okay, this is actually really big. And this should answer some questions a lot of you have had. So some of you have even asked me about it, and we talked about it separately. But this should actually answer some very unsettling things you might have thought about. You might have thought, oh gosh, like all this discrete math stuff, we're supposed to prove things from the bedrock. It's all a bunch of baloney because I found some mistakes already. I found some contradictions. No, we did not. We're gonna prove why today. So anyway, any questions before I start? Okay, time to go. I just got the cue. So we are on air, everybody. Welcome back to Discrete Math. And today we're going to finish up section 3.1. Check it out. I didn't even tell you. I didn't even mumble in my breath what I'm doing when I change the cameras. There we go. So, yes, today we're finishing up section 3. Oh, you can't see that at all. There we go. So section 3.1. I'm going to change this setup. There we go. And that is all about, right? This is all about predicates and things like that, right? This started out with saying, you know, statements are kind of limiting. Let's throw a variable in there, right? That's exactly what we're doing now. So first off, before you do the exciting part, let's just kind of finish up, shore up some of the things we were doing last time, and work on being able to translate English statements into logic. So let's say, we got a more exciting color. What are we doing? It's a Tuesday. Tuesday for purple. We should use Mardi Gras colors today. Okay. It might be exactly like 6 months to Mardi Gras. Maybe. That could be cool. Anyway, so that sounds right? So let's work on translating English to what I'm going to call logisteri, which is like all those made-up nerd languages, but more mathy. It just translates into logic. So, for example, if I had the statements, every natural number is a real number. how would you write that logically? There's me slowly dancing. Help. So every natural number is a real number. Well, every. Come on, what's that?
For all that?
For all, right? This screams of a for all statement, right? So what this is saying is that for all, right? And for all what? For all natural numbers. But remember with these for all statements and things like that, for all statements, this is a universal statement. Universal statements all go like this. They all say that for all x in some domain, we have a predicate being true, right? This is what a universal statement does. And what's really happening here is they take a statement like every natural number is a real number, and instead of looking at every natural number at once, instead it looks at a particular one. So this is saying for any particular x in the domain, p of x is true. But that's the same thing as saying for everything in the domain, p of x is true. But it's much better to look at one number because then one element, because then we can actually kind of talk about it. We can talk about this one element, where we can't really talk about every natural number at once, but we can't talk about any particular one, right? Hope that makes sense. If it works for any, that means it works for every. That should be obvious, but it's kind of a subtle point, but important point. So this is saying for all, let's say little n in the big N. And this symbol N with a bar, this means natural numbers. So this corresponds to this. For all of the natural numbers, N is in that, which is the real numbers right there. And by the way, is this true?
Yes.
Yeah. Because we have the chat's blowing up. Oh, that's been just answering all my questions. Thank you. Yeah. Thanks, Benet. You got totally right. Yeah. So the other thing is that for all in the natural numbers is in the real numbers, which is true. Now we could not prove this with method of exhaustion quite because there's infinitely many natural numbers. That would be quite exhausting to go through and prove for all of them. You couldn't even do it. You ran out of time. We're all mortal. I don't want to make a question of mortality, but you kind of kick the bucket before you check every single natural number, and I would too. But actually, I wouldn't because I know a different method. But the point is, method of exhaustion is not going to work. But still, the same idea holds. The same idea is that this means every natural number is in fact a real number, and there is ways to verify that. Not really verify. There is ways to prove that, but we will talk about them in a later video. Anyway, so let's do another example. Another example would be some multiple of 4 is a multiple of 3. And I will call being a multiple of 4, right? The set of all multiples of 4, I'll call that, or I'll call x being a multiple of 4, this predicate m of x. Maybe I'll say m4 of x, as someone mentioned last time. I'll call being a multiple of 3, m3 of x. So basically, m4 of x is true if x is a multiple of 4, false everywhere else. M3 of x is true if x is a multiple of 3, false everywhere else. This isn't really standard notation, but I like it. Actually, the standard notation for this would be x in 4z. You can write it like that. But we're not there yet, so let's do this. So, how can I write this in logic, in the ancient language of the logic elves, logisterian? Oh, I give it away. Crap. Okay. Anyway, yeah, so the sum here, the sum multiple of 4 is multiple of 3. That's saying sum doesn't mean that everyone works. This means sum. It means there's at least one, right? This is saying there exists, right? There exists, let's pick a letter. Let's say an M. In M of 4, such that, oh, so actually no. This is actually good. I made a mistake. I made a mistake here, but this actually come up later. So remember this example. So if I'm saying some multiple of 4 is a multiple of 3, this is a multiple of 3. This M3 is still fine. That's saying something about, like I want to be able to plug in an X, and it'll tell me if it's a multiple of 3 or not. True if it's multiple of 3, false otherwise. But multiple of 4, I kind of want that to be my domain. So I don't really want that to be a predicate. I just want that to be a straight up set. So I'm going to call this set, I'm just going to call it D. So this is saying there exists an M in D such that M3 of M is true. So there's just an M in D such that M is in fact a multiple of 3. So another way we could have written this is that, like, if you made is a real number, if you made that predicate like R of N is a real number, then you can replace this with R of N if you wanted to. Right? It doesn't really matter. The important part is to recognize N is in R. That's a predicate, right? It's true depending on what N is. You got to plug it in. I feel like I'm talking a lot, but I hope this makes sense. We're kind of going over different ways you can write all this kind of stuff. Any questions? Okay, so next, let's say we have, oh, by the way, is this true or false?
Also true.
Also true. And we can use prove, I'll say, can prove with 12 as an example. Because 12 is a multiple of 3 and a multiple of 4. All right. Let's do at least one natural number is a real number. So, is it a universal statement or an existential statement?
Existential.
Existential, right? He's saying that the claim it's making about the natural numbers is just at least one of them. It's just saying about one of them, not all of them. So there exists an N in the natural numbers such that N's a real number. So you could say N is a real number, or if you want to name that predicate R of N, you could also say R of N. Doesn't matter. But yeah, is this true or false?
True.
True, right? Can prove with 1, for example. It'll totally work. The point is here, what I wanted to get at is that we kind of talk about how for all and their existence have this kind of yin-yang relationship. They're kind of opposites in the sense that the opposite of a universal statement is an existential statement. The opposite of an existential statement is a universal statement. And they're also, that kind of makes sense because they're kind of saying opposite things, kind of like the opposite of all of them is like one of them in a certain sense. But they're not, that's why I use the word yin-yang because they're opposite, because they're not quite opposite. It's kind of like how and or aren't quite opposite. So they have this yin-yang thing going on where just because for all in an N is an R, doesn't mean that there doesn't exist one. In fact, it does mean, right? If it works for all N, it's going to work for at least one N, right? These statements are the same thing except for the quantifier. And also notice that if it works for there exists, it doesn't mean it doesn't work for the for all. It might work for the for all, it might not. Does that make sense?
Yeah.
Someone unmuted and then muted, so I think that means yes. Okay, so let's move on. Let's say, what if we have sine of x equals 0 for all x multiples of pi. All right. Maybe I'll say whole numbered multiples of pi. And I will label this predicate P of x. So P of x equals, or equivalent to x is a whole numbered multiple of pi. All right. So what's the statement equivalent to? Is this a universal statement or an existential statement?
Universal.
Universal, exactly, because we have this for all. And what's our domain here, Safa?
It's. I think it's
I'll give you a hint. I kind of made it
pi,
again.
like those whole numbered pies.
Those whole multiples of pi. Yeah, I don't really want to make this a predicate. I kind of want to make this a domain instead, although we're going to come back to this. So I'm going to make it a domain instead. So this is saying for all x in this domain right here, we're going to label something else. I'll label it for all x in this, I'll label it big pi. For all x in this domain, big pi, sine of x equals 0. So notice that sometimes in English, right, we kind of put the predicate first. This is kind of like those movies that get to like the most exciting part, where they go like, where like you see someone getting shot, and then it goes 3 days earlier. So like that's what this is. It's going sine of x equals 0. Isn't that interesting? Well, which x is? For all x's, they're holding multiples of pi, right? They kind of backfill what they're talking about in here. So that's why in logic we always put the universal quantifier. We always put the quantifier first, then the domain, then the predicate. Sometimes in English we kind of mix those things around, but it's important to know which ones are which, and I put them in order. So let's say we have, last one I'll do is A is odd if A plus 1 is even for all multiples, sorry, no, for all integers A. All right. So is this universal or existential?
Universal.
Exactly. So we have a for all, and then we're using a, keep the variable A. So for all A, and what's our domain? What are we talking about here?
Integers A.
Integers A, right? We're making it clear about the integers, all the integers. So for all A and Z, this is a symbol for the integers. It's a Z. We'll talk about that again, but it'll be nice to have a little practice. So for all A in the integer Z, and then what's my statement going to be? Or what's our predicate going to be?
A is odd if A plus 1 is even.
True. We could kind of write it like that.
Could you say A is an element of the set twice Z minus 1 or something like that?
Oh, I'm trying to do odd.
Yeah.
You're saying,
Oh wait, am I?
yeah, odd. The odd integers.
Oh, I'm not actually reading. I'm sorry.
The odd integers can't be written like this. That's actually totally fine notation. But we'll go over all that later. But what I'm more getting at is that, so remember, a predicate becomes a statement if you plug in a variable. If you plug this in for the variable, right? So if you plug this in for A here, this is clearly a predicate. But if you plug this in for A, what kind of statement do you get? It's a very special statement.
If then?
If then, right? Like right now it's a predicate, but if you plug anything in, you get an if then statement. But normally are if-then statements written in this order? What's the hypothesis here? What's the conclusion here? For example, is this saying that A is odd implies A plus 1 is even? Or is this saying A plus 1 is even implies A is odd?
The latter.
The latter. This is saying this guy right here. This is saying A is odd if A plus 1 is even. A is odd is conditional on A plus 1 being even. Right? So this kind of if statement kind of flipped on its head. Another weird thing we do in English all the time. Right? But the way you can write it down here, but the way it would make sense as in logic would be saying A plus 1 is even implies A is odd. That's what this is saying. Because this says if A plus 1 is even, then A is odd. So the way you can write that is A is odd. I'm sorry. We just talked about this. You can say A plus 1 is even implies A is odd. And so notice it's kind of nice that like this whole thing is a predicate, but you kind of think of it as like a conditional predicate. It becomes a conditional statement if you plug anything in. But just like a conditional statement as a hypothesis and a conclusion, and here the hypothesis and conclusion both are also predicates. But so it's kind of weird. It's kind of like you did a conditional statement, but every word there's a statement you replace with a predicate. I don't know. It's kind of fun. But anyway, yeah, you have this right here. And this is going to be true. And the way you prove it true is you have to prove it true for every single A plus 1 that's even. For every single integer in the thing. Cool. Any questions on that? Well, good, because you'll have a lot more of this to do on your homework. But honestly, it's like, I mean, this stuff is cool. This stuff is the basic stuff. This stuff is kind of like just the stage of understanding what a question's asking. All right. Yes. It's finally getting to the moment we've all been waiting for, and you didn't even know you're waiting for it. After you hear this, you'll be like, I didn't know I was waiting for that my entire life. Everything makes sense now. Yes. Although I don't know if I want the world to make sense. I like the mystery. But the point is, here's the mystery. If the rock is bald, then the rock is in Moana, the Disney movie Moana. If the rock is bald, then the rock in the Disney movie Moana. You could think of this as a statement P, the rock is bald, as a statement. You think of this as a statement Q, the rock is in Moana, as a statement. So you can think of this as the equivalent to P implies Q. Whether you think about it in the English form or you think about it in the logic form, is this statement true or false?
True.
True. The rock is bald, and the rock is in Moana. P is true, Q is true. So our function, so maybe you should look at it like the if-then function of PQ, which if you plug in what we know P and Q are, P is true, Q is true. That's the first row in our truth table, and that gives us true. Does this unsettle anyone else?
Well, the rock's baldness doesn't actually imply that he's in Moana, right?
Yes. This is why it's so unsettling, because for P, we say P implies Q. We say if P, then Q. We like to think of this as sort of a deduction. We like to think of this, I told you guys that. I bold-faced, looked my webcam in the eye, that it could theoretically be looking you in the eye, and I said that this kind of represents deduction, that word kind of is key, because it doesn't really represent deduction. All this says all P imply Q says is if P is true, Q will follow. In this specific instance. So if P is true, then Q will follow in this specific instance, right? Here, we're saying the rock is bald, then the rock is in Moana. We're talking about an incredibly specific situation. We're just talking about the rock. The point is, if P is true, with one data point could be a coincidence. I might have spelled coincidence right. Anyway, yeah, this is a coincidence, right? I mean, it is true that the rock is bald, and it is true the rock is Moana, but that really has nothing to do with each other. It's just a coincidence. But the problem is, our universe here is just the rock, right? And so our statement is just kind of looking at this one tunnel vision. It just looks at the rock and it goes, hell, the rock is bald, the rock is Moana. As far as this statement is concerned, the only human in existence is the rock. Therefore, if the rock is bald, then the rock is Moana, right? So here's the point. In order to, when us as humans hear this statement, if the rock is bald, the rock is Moana, what we're thinking is that the rock being bald has something to do with the rock being in Moana. That we can deduce the rock is in Moana based on the fact the rock is bald. What we're really saying when we say this deduction thing is it must have, like, we really think it has something to do with the rock. But it has everything to do with the rock in this case. But what I'm saying is, what do we kind of think that this statement's really saying? Or I'm saying that with one data point, this is like a coincidence. How could we open up the universe and actually see what's going on here?
Introduce variables, so these are stated in predicates.
Yeah. Instead of just looking at the rock, what if we say for all x in the set of actors, if x is bald, or maybe I'll say x is bald implies x is in Moana. Is this true or false?
False, but I can't
False.
think of a counterexample because I don't know
Vin
any
Diesel.
bold actors. Okay, cool. That works.
Counterexample, Vin Diesel or any other bald actor you can think of. Yeah. Kevin Hart, right? Like yeah, all these guys. So yes, this there down here for all x and actors, x is bald implies x is in Moana. Once we introduce x, we're opening up our universe not from just the rock, but all actors. So this really is saying that x being bald has something to do with x being in Moana, which is why it's false. Because being bald has nothing to do with being in Moana. But when you open up your universe like this, right, this is no longer fooled by coincidences. When we have all actors as data points, our statements no longer fooled by coincidences. So it truly is a deduction. Is this making any sense? I mean, this is kind of like if your only data point, if the only planet you ever saw was the Earth, right? You'd say, okay, you'd think, okay, all planets have life. So you'd say, like, you know, if the Earth is the only planet, you'd say, if the planet is the Earth, then it has life, or something like that, right? Or, yeah. But once you get more data points, you start to see the bigger picture. If you're just looking at the rock, you might think, okay, if you're bald, you're Moana. But if you're looking at all actors, you see how ridiculous this is. Because most actors that are bald are not in Moana. And probably only one, right? Who's got questions on this? Is it because it's too easy or too hard? So this is a very, very, very important topic right here. This is kind of what we've been leading to with Dave with this predicate stuff and all that. Let's do some examples, maybe. And I'll say these guys are called universal. Oh, 3 questions. Oh, that's insane. Interesting. I did not know Venus has life. Organic compounds, I'm sorry. So these are called universal, speaking of the universe, universal conditional statements. Because remember, if-then statements are called conditional statements, but now instead of, it is cool. But yes, these are universal conditional statements. But now instead of making a conditional statement about one specific thing, one data point, just the rock, now you make a conditional statement about an entire universe, about an entire domain. So for example, you could have if x squared is even, then x will be even for all x integers, right? And the way you write this, first of all, this is a universal statement, right? Because it says for all x integers. So what this is equivalent to is for all x in the integers, x squared is even implies x is even. All right, and then this bad boy, true or false? What do you guys think?
True. True.
True. It is true that whenever x squared is even, x will be even. But does x squared being even cause x to be even?
I think it's the other way around, right? It just so happens to be a like biconditional statement, but
Yeah. So this is weird. If anything, if you're kind of talking about cause and effect, it's kind of the other way around. It's kind of like if x is even, you know x squared is going to be even. And so what that means is that if x squared is even, it had to come from an even x. But anyway, the point is conditional statements, we talked about this before, but universal conditional statements are the same. They don't have to be cause and effect. Maybe a better example would be if we said, if if let's say B is a human or is a living human, then B has blood. For all, well, yeah, we just leave it at that. Because the English statements don't always kind of do their domain right. So this is a valid English statement. And the way you'd write it in math terms, you could say for all be humans, or be in the domain of humans.
Should it be living humans? Do dead humans still have blood? Do they count?
Well, it doesn't really matter here, right? Because I'm making a statement about living humans, you know?
Okay.
Yeah.
Oh,
I'm not
okay,
saying
that's
that
true.
like nowhere in the statement am I saying dead humans don't have blood.
Hmm,
Living
that's
humans
true.
definitely have blood. So for all B humans, if B is alive, then B has blood. This is a weird thing, but I was trying to think of something like this. I was trying to think of like, okay, like there's just so many weird, there's so many interesting people out there. I was trying to think, okay, like maybe if you have feet, like I was trying to think, okay, B has feet, then B has legs. Well, maybe not. I've seen that person that has feet that are kind of attached to their hips. But anyway, the point is, I think this one's safe. I think if you are alive, if B is a human alive, then B must have blood. And then the way you can write this more mathy is with the arrows of the if then, right, with the implies. The point is here, does being alive cause you to have blood?
I mean, sort of, right? Like blood is produced as a function of being alive.
That's actually a good point. It's circular. Maybe I should say, let's go back to the classic. The classic. If B is a living human, then B was born. Does being alive cause you to be born?
No, quite the
No.
opposite, actually.
Quite the opposite. Being born causes you to be alive. But if you are alive, we can deduce that you must have been born. So these if things are not cause and effect. Not cause and effect, but we can deduce you were born, or maybe say, but yeah, we can deduce someone was born from the fact they are alive. That's the cool thing about deductions. It can be cause and effect, but it doesn't have to be. It can just be that I know you were born because you're alive. Neat, right? Because all it's saying is that anyone that's alive was born. You know, whenever this is true, this will follow. Interesting, right? I think it's interesting. The point is here that this is a kind of real true deduction because it's saying something about all humans. It's making a claim about all people. When we didn't have the B here, if we just had like Jeff is alive implies Jeff was born. That's great for Jeff, but this just says something about Jeff. It's possible it's a coincidence. Our universe is too small. Our universe is just Jeff. It's just a statement about Jeff. right? So we shouldn't think of any dependency at all here, right? Because we don't have anything to have a counterexample. We don't have, we're not saying anything about a general statement. We're just saying something about Jeff. This is actually saying something about all humans. That's why we can be sure that it's more of a deduction, more of a dependency happening, because we have a lot more data points. We're saying this is true for all of these data points. Is that making some sense? I hope the data points thing kind of helps a little bit, because it reminds you a little bit of maybe statistics, where it's like you need a few data points to actually see a pattern. It's not enough to say the rock's ball, the rock's in Moana, therefore everyone's ball is in Moana. No, you need to see a lot more, right? Now in statistics, the difference is you can never check your whole universe. In statistics, you can't check every human, right? And check every bald human and see if they're in Moana or not. There's way too many, right? But in statistics, what you could do is you check a lot and then you kind of make a good educated guess using probabilities. But that's not what we're doing here, right? We're doing straight up math. And so we can make our universe everything. We can make our universe infinitely big if we want. So our universe is really, in the rock Moana example, if we're going to the bigger universe, we're considering all possible actors. Because we can do that with math. It's just symbols on the page, but it's powerful. Yeah, let's do more. So if I said, if X is an American citizen, or yeah, if I said if someone is an American citizen, then they are brown haired. I would just write this in terms of math. Well, first of all, it's a universal statement, right? You just say something about all Americans. So this is saying that for all people, so for all X and people, X, an American citizen, implies X has brown hair. Is this true or false?
False.
I agree. I can prove it. I have brown hair. I'm American. In this room, it looks like pretty much all Americans have brown hair.
The U.S. president has non-brown hair.
The U.S. president would work. Brad Pitt would work. Right? Yeah. Let's go with, can we name a single famous American redhead? Oh, that bums me out. Who's got me? Bryce Dallas Howard. But anyway. Yeah. Wow, there's not a lot, is there? I'll use Brad Pitt, for example. He's a blonde, right? Or I'll use Jennifer Aniston. Jennifer Aniston's blonde, right? You know what I'm trying to say, right? The answer to this is false. Counterexample, right, would be Brad Pitt is American and blonde. Hence, there is an X and people, mainly Brad Pitt, is such that X, an American citizen, I should have written US this whole time, implies X has brown hair is false, right? So the point is, the reason this is false, is because we can find a specific X, we can find one counterexample for X that we can put into this predicate and make the predicate false. Remember, this whole thing's a predicate right here. All right. The point is, though, that Daniel Valvo has brown hair, implies Daniel Valvo is a U.S. citizen. I have brown hair, I'm an American citizen, I'm not going to get my passport for you. But the point is, this is true. And this should no longer be as unsettling. I hope it's not. Because even though it's true for me, Daniel Valvo, that's just because our universe is so tiny, this is a coincidence. It does happen that I have brown hair, and it does follow that I'm a U.S. citizen. It happens to happen in this case because we're just looking at Daniel Valvo. But we're not saying something about all people. This is saying something about all people. Does the difference here make sense? Talk to me, people. Talk to me. Well, I want to know how I feel about this because it's legitimately an unsettling thing. I mean, we had that in the homework, right? Where I gave you guys that one example where it was like there's only 5 dogs in Blacksburg implies the world is round is true or something like that, right? And that's incredibly unsettling because those two facts had nothing to do with each other. But the problem is, once again, our universe was so small. We're just talking about this specific case of things, right? Whereas in order to actually see a deduction, in order to actually think about this, in order to actually think that having brown hair has anything to do with being a U.S. citizen, you have to vary your subject. You have to vary your subject to see if it works for all of them. That's what it means to have a deduction. That's what it means for brown hair to actually imply you're a U.S. citizen. It has to work for everybody, right? It does not just have to work for one person. I think that makes sense. I think so. Let's write this in big red letters. In order to say that property P of something implies property Q, you have to consider subjects in all of the domain, not just one.
I have a question.
And then once you have that, it is true that property P implies property Q. Here, Daniel Valvo has brown hair, means Daniel Valvo is a U.S. citizen. That doesn't mean anything about having brown hair implying you're a U.S. citizen. It just says Daniel Valvo having brown hair implies Daniel Valvo is a U.S. citizen because they both happen to be true facts.
Quick question.
What?
Quick question.
Yeah.
So is this meaningfully different from the case where the domain only has one element, Daniel Valvo?
You know, it kind of depends how you look at it. So you're saying like what if the statement was for all X in Daniel Valvo, if X has brown hair, that implies X is U.S. citizen. Is that what you're saying?
Yeah.
It is meaningful different because again, this is just saying something about Daniel Valvo. You know what I mean? Your universe is one data point. It's really small. This right here, if you actually want to talk about the property, right? If you want to talk about the property itself, if you want to talk about the property, oh wait, these are backwards. Oh, well, you see my point. If you want to talk about the property of being an American citizen, I'm gonna flip these. Is a U.S. citizen is a U.S. citizen. Daniel Valvo has brown hair. So the point is, if you want to talk about these properties, if you want to talk about the property of being a U.S. citizen, it implies that it also must have the property of having brown hair. If you want to say the properties imply each other, that means the subject shouldn't matter. And so if the subject doesn't matter, your domain can be as general as you want it to be, all people, right? But if it works for all people, then you know what it was the property. It was the properties that are important. But if your domain has to be really tiny, if you're just looking at one specific thing, this really isn't saying anything about the properties. It's saying something more about the person itself. Does that make sense?
I mean, it does, but like it still doesn't really like chase away the idea that this isn't quite exactly implies, right? Like
Well,
it
you know what?
becomes more and more
I'll
true
give
the
you a
bigger
better
a domain
example of
gets,
that.
right? But like
A better example of that would be this right here. If you say, if I have, or I'll say if X has an even number of children, then the world is round. Right? What you can write in math as, like, if you call this P of X, you call this Q of X, this is equivalent to saying for all X in people, P of X implies Q of X. And the problem is, this is true. The problem is this is true right here. And the number of children any person has does not affect the shape of the world. It turns out these are totally independent facts, right? But it's true because for any X you plug in here, right, whenever P is true, Q is going to be true. Why? Because Q is always true. Remember, P implies Q is equivalent to not P or Q. So you can write this as for all X in people, not P of X or Q of X. And since this Q of X, like the X doesn't even show up here, right? There's not even an X here. There's like a constant function, like f of X equals 1 or something like that, right? Like that function right there, it doesn't matter what X is, it's a constant. Same here, this is a constant. The world is round, it's totally independent of if you have children or not. The X doesn't even show up. But this is always true. It's basically, it's a tautology basically, right? And so this is always true no matter what the hell X is. And so what that means is you're always gonna have the or Q of X be true. But anyway, the point is this statement right here will always be true. And it has really nothing to do with X. So in this case, it's not really saying there's a dependence, but the reason for that is because there's kind of no X here. This is cheating a little bit. If you make one of your statements a tautology. But if both of your statements really do have X in them, then you really are making a deduction because you're saying that this predicate, and a predicate is really, what is it? It's just a property that's kind of disembodied from its subject. Right? This is saying if X has any even number of children, this is X has any even number of children. The properties have an even number of children. What's the subject? Doesn't matter. It's just X. We'll plug it in later. Right? So this truly is kind of studying the idea of a property. If you have a property, if you have a predicate here, it implies a predicate here. And they both truly do have something to do with X. They're not tautology. They're sometimes true, they're sometimes false, depending on what X is. Then you really do have some sort of deduction because you're saying that whenever X is property P, it's also going to have property Q. So there is kind of a dependence there, at least for whatever your domain is. I feel like I'm ranting. Is this at least interesting to people? It's a great question. It's a great question. And it's kind of like, it kind of just depends. This depends a little bit on your perspective, because all these things have strict mathematical definitions. And I'm kind of trying to give you a little bit of intuition. I'm trying to kind of give you a little bit of intuition for it and how mathematicians like to think about it. But the point is, if you have a different perspective, you'll think about it differently. And that's totally fine, right? As long as we agree on the underlying truth table and all that definitions, we can still do math together. So whether or not you think about this as truly being a deduction, or whether or not you just think about this as more of just an if-then function applied to a larger domain, right? Doesn't matter. The point is a general universal conditional statement saying that for every X in a domain, whenever the hypothesis predicate happens, then the conclusion predicate must happen. All right. And those are some of the most important. That's arguably the most important statement in math, because everything we do from now on will basically be universal statements. We'll be trying to prove things about, because remember, in math, we're trying to link statements. So like we're trying to prove things about all even numbers. We're trying to prove that if X is an even number, then X is some other property. If X is multiple of 4, X is some other property. If X is a prime number, we know this. If X is like, it's all gonna be about that. Any questions?
So one more thing is, what about the case where every X in the domain is going to evaluate false and...
So then you're always vacuously true.
Right, okay.
That's another good question. So let's say we had for all X in people, X is a dog implies X is a doctor. This is true. Because for all X in people, right, X being a dog is going to be false. It's never going to be true. So this statement's always going to be vacuously true. You can prove, you can kind of make a proof. You can say, let X in people, then X is a dog equals false. So X is a dog implies X is a doctor is going to be true. All right, that would kind of be your proof. The point is you're proving for any particular person, this is true, so for every person it's true. The point is though, this is kind of like the whole pigs fly thing again. It's like, you know, we said like, if pigs fly, then I'll give you $1 million kind of thing. It's like, it doesn't really matter what you say after the if pigs fly, because it's not going to happen. You know what I mean? It's kind of a meaningless statement. That's how I would think about that.
Is there like a notation for none? Like for no elements or?
For vacuously true?
No, like, you know how there's like the for all, like the upside down A, but like,
Yeah.
is there a for none?
Oh,
Like
for
for
none?
nothing?
So the way you would write for none, so if you want to say, instead of saying for all people, you want to write for no people, you would say, what you'd say is you make a there exists statement and then negate it. Because if you're saying there does not exist, that means it's for none.
Okay.
But we'll get to that later. So real quick, before we leave, got a little sidetracked. Let's talk about these if-then statements and these domains and kind of different ways or equivalent ways you could write things. So for example, before I wrote that if x is even, we said if, or if the statement was every square of an even number is even. Every square of an even number is even. There's a few different ways you could write that. You could write that as saying for all x, in the integers, x even implies, actually this is a different statement I wrote before, but it's a statement in itself. X squared, right? Every square of an even number is even. That's saying for all integers, if x is even, then x squared is even. But here's a question. Do we even need a conditional statement to write this? Could you think of a way to write an equivalent statement here without using an implication arrow, without using an if-then? I'll give you a hint. Here we took the domain to be all the integers, and then we said, for this specific part of the domain, we know whenever this is true, this will follow. But what if we change the domain?
Can you define it as like 2z?
Yeah. I'll just say for all x in the even numbers, so the set of even numbers, x squared is even. Right? These two things are saying the same thing. Because here we restrict the domain to begin with. And here we have a more broad domain, but then say for this particular part of it, we have something. That's kind of interesting. There's always multiple ways to write these things with if-then statements. So what if I said for all x in 2, 4, 6, I'm going to say in 2, 4, 30, 1, for any 2, 4, 31, for any number in 2, 4, and 31, if it is less than 10, it is even. So this is a universal statement, right? You could write it as for all x in 2, 4, 31, x less than 10 implies x is even, right? That's kind of a direct translation of what you're saying. What's the other thing you could do?
You could have the domain just be 2 and 4.
Yeah, I just use it simpler. Yeah, I mean, you could just restrict the domain to begin with. For all x in 2, 4, x is even. The point is, if you have any universal conditional statement like this, you could write it as just a straight up universal statement. If you change your domain to be just the places where the hypothesis is true. So if you make the domain, so if you have for all x in D, P of x implies Q of x, this is equivalent to for all x in, so I want to say what here? For all x in what? Q of x is true. Well, for all x in the things that can plug into P of x and get true, right? All x in the hypothesis, the hypothesis predicate true. But what do we call the set of all things that make a predicate true?
Truth set.
Truth set. Exactly. For all x in the truth set of P with domain D. So you can always do that. You can just restrict your domain to be the truth set of the predicate, right? And then, well, this is saying that whenever P is true, Q is going to be true. So if you restrict it right away to be the truth set of the predicate, you know it makes it true, so Q of x has to be true. It's kind of skipping a step. The point is, you can always do this if way to write conditionals. But anyway, I'm over time, so we're done. Any questions?
Another question I had is, does the introduction of variables change the validity of any of the argument forms that we've learned?
Good question. The answer is no, because these variables, right, you still end up, like argument forms, right? So for example, if you had like elimination, right? So elimination says that P and Q, and if you know that not P, therefore you can conclude that Q must be true, right? This is the argument form. But remember, these variables, you know, you make predicates out of them, but you can't put a predicate in here. Oh, I see what you're saying a little bit.
I mean, I think, like, I agree with you. I think it's also still true because you can just evaluate for every point, like every point in the domain, right?
Exactly.
And do it individually.
So this right here, is still totally true, just because for all x and D, right? If for each x, if it makes the premises true, right? I mean, once you plug them in, you get actual statements here. Once you get you're writing here. So yeah, so it kind of doesn't matter because you're always going to convert them to statements before you actually make an argument, kind of. Yeah. Anything else? These are great questions.
Wait, but actually, doesn't that change things? Because sometimes the premises might not be true anymore because of the particular x you plugged in.
Right, but when the premises aren't true, you can no longer make the argument. So the P and Q and not P, therefore Q, this is only saying something about the case where the premises are true. So for example, if you can prove, if we know for all x and D, P of x and Q of x equals true, and not P of x equals true. If you know that going in, meaning you know your premises are satisfied, then for all x and D, Q of x is true by that argument. So you say for all x and D, so for all x and D, I mean, you can kind of do this. So your premises have to be satisfied still. So you have to know you're going to satisfy them.
So like to do this type of argument, you have to be very specific in defining your domain to be equal to the truth set, basically.
Yes, exactly. Exactly. And what's oftentimes going to happen in math is you might not know everything your domain satisfies the premises, but what you will know is that you can split your domain up, and you can work on cases. You can divide into cases. And so a very nice trick is a lot of times you'll say that, for example, like, what's a good example? I don't know off the top of my head, but the point is, or if you want to say that, like, if you want to say x squared minus x is always even. It's kind of not clear as looking at it why that's true. But if you prove it, you divide into cases when x is even and x is odd, and then it becomes obvious. Because when x is even, x squared is even minus even is even. When x is odd, x squared is odd, x is odd minus odd is even, right? And so you can always say it's even. So the point is, you can split the cases and show that just part of your domain makes the premises true. Then use the argument on that part, and then for the other part of your domain, you can make a different argument to get to the same spot. But yeah, these are all great questions. Yeah, and class is over, by the way. We're just talking now.
Should you stop recording?
Well, these were good math questions, so I wanted to record so people at home and their
Oh, okay.
could kind of get these answers as well. Anybody have any other interesting math questions? Okay, well then I'll stop recording.